Welcome everyone. Thanks for joining us for our 99th episode of This is CDR. For those of you who might be new to us, This is CDR is an online event series that explores the wide range of carbon dioxide removal or CDR solutions, which are currently being researched, developed, and deployed, and contextualize them for policy proposals that we seek to advance at every level of government, both in the US as well as in national and subnational jurisdictions globally. My name is Megha Raghavan, and I'm an OpenAir member based in London, and I work on policy and market development. If you're new to OpenAir is a distributed volunteer network dedicated to the responsible advancement of carbon dioxide removal solutions essential to solving the climate crisis. And I think Chris Neidl, one of the founders of OpenAir, will be in the chat sort of putting in some links if you're interested in joining or learning more. OpenAir's growing global community collaborates on shared open source missions in the areas of policy, innovation, communications, and activist market development. So please check it out online and come join us. Here's just a sample of a few of the many missions that in carbon removal that OpenAir is working on. And so you can see they really span huge range of parts of the world, as well as different types of projects. So please check them out if you're interested in joining one of these existing missions, or maybe even leading a mission of your own. OpenAir collaborates in a very open way. People are always coming up with new ways of advancing carbon removal and setting up missions. So check out the website and look there if you want to learn more or set up a mission of your own. Just a couple of really important missions that OpenAir is working on right now. So right now we're putting together a citizen lobbying campaign for the Massachusetts Carbon Dioxide Removal Leadership Act. So if you're interested in getting involved in that, that's moving forward, which is really exciting. We also have citizen lobbying for the California CDR MDA, which is moving forward in that state as well. So if you're in one of those states and want to get involved in the lobbying efforts or just want to learn more, I think Chris will be putting links in the chat where you can find out more on both of those. For anyone new to CDR, we tend to define as all anthropogenic activities that remove CO2 from the atmosphere and durably store it in geological, terrestrial, or ocean reservoirs or in products. That definition comes from the CDR primer, which is a really great resource for anyone looking to get up to speed on the different CDR pathways and sort of the context around CDR. So I believe there will be a link to that as well. It's a great resource for anyone looking to learn more. Okay, I'm going to hand it over to my colleague Tank to talk about our presenters and the run of show. So Tank, whenever you're ready, please come on.
Hi everyone, I'm Tank, based in Taiwan. I'm an OpenAir member, works on communications. Some housekeeping notes before we start. Our format will be a short presentation followed by a few prepared questions, then moderated audience Q&A. So please type any questions you have into the Zoom Q&A box as we go along. That's not the chat box, but the Zoom Q&A box. Also, this event is being recorded. We will send the video link to everyone who registered and also post to OpenAir's website and YouTube channel. This week, we're pleased to welcome CEO Barclay Rogers and CTO Dr. Hannah Murnen from Graphyte to discuss the company's carbon casting process, which leverages residual biomass for permanent, affordable, and scalable CDR. Barclay Rogers is a seasoned executive with extensive carbon experience, including leading business development efforts for Indigo Agriculture, agricultural soil carbon removal, and overall development activities for C12 Energy, geologic carbon sequestration. Barclay holds an MBA from the University of Cambridge, an LLM from the University of Arkansas, a JD from Lewis and Clark College, and a Bachelor of Science in Mechanical Engineering from the University of Arkansas. Dr. Hannah Murnen is a proven leader in developing and scaling industrial technologies. She served as the Managing Director of Activate Anywhere and Chief Technical Officer at Compact Membrane Systems. Hannah also spent several years with McKinsey and Company, advising industrial companies on growth strategies and operations. Hannah holds a PhD in chemical engineering from the University of California Berkeley and a Bachelor of Engineering from Dartmouth College. So Hannah and Barclay, when you're ready, please turn on your video, introduce yourself, and take it away.
All right. Well, hi, I'm Barclay. Thanks so much for the introduction. And Hannah, you're on the screen as well. There you are.
Yeah.
All right.
I'm just pulling up the slides. Can you all see them? Can you see them, Barclay?
Very well. Thank you. So just wanted to thank everybody for attending. It's an exciting opportunity for us. Looking forward to sharing with you some information about graphite, what we're doing through our carbon casting process, and most importantly, looking forward to answering your questions. So we'll kick off with a short presentation and then get to the Q&A as quickly as possible. So just quickly on graphite, what we are endeavoring to do is to become the largest supplier of durable carbon removals in the world. So a quick snapshot of where we are today is we've developed a process that we call carbon casting. And I think the most sort of important thing there is that the cost of production for permanent carbon removals is under $100 a ton of CO2e. As we'll talk about later, that's a really important benchmark for the industry as a whole. We're also moving quite quickly. Graphyte was founded in February of 2023, and we are actually right now have turned our initial project on. It's a project in Arkansas that we call the Lava project, and we will sequester 15,000 tons of carbon dioxide this year, in 2024. That's demonstrating sort of the scalability of our process. And then finally, where are we trying to go is we're looking to make a meaningful impact on climate change. And what that means is we have a practical plan to get to 10 million tons of CO2 removals by 2030. So that's us in a nutshell. Let's jump to the next slide. So, one of the things that I think is really important for us all to just really understand, grapple with, think about is the speed with which CDR needs to scale. Okay, so this is just looking quickly at the graph here on your left. This is the World Resources Institute calling for 350 million tons of carbon dioxide removals by 2030. Right, so that would imply basically if you took where we are today and looked at the necessary growth rate to reach that, we'd need to grow as an industry by about 150% per year. Okay, so then let's just kind of make that a comparison to electric vehicles, right? If you think about the broad initiatives to decarbonize the economy, electric vehicles, arguably one of the big success stories there, right? And you look at the rate of growth in the EV space over the past 7 years, right? That's the gray line on the bar below. And you would see we need to grow at about 3 times the rate of electrical vehicle adoption over the past 7 years. Okay, it's just giving you a sense of the challenge ahead of us as an industry and the need to scale very rapidly. Go to the next slide. Just a little bit on the kind of durable versus if you will, non-durable. It's kind of versions of carbon removal, right? So as the listeners here probably know, there's various forms by which carbon dioxide can be removed from the atmosphere. And when people talk about durable carbon dioxide removal, what they're primarily talking about is 2 things. One is the certainty of measurement associated with the removal, right? And is how clear are you that actually like a ton of carbon dioxide has left the environment and left the atmosphere and is permanently stored somewhere. And then second is permanence, right? And that is the concept that the carbon will remain out of the atmosphere for 1,000 years or more. One of the thoughts here is that when you think about why there's such focus on durable carbon removals, it's that this current state of the voluntary carbon market is candidly a bit of a mess, right? That is that people aren't so certain whether carbon dioxide is actually being removed from some of the existing techniques. They're not quite clear how long it's going to stay out of the atmosphere. So there's been this big shift. You can kind of see in the box in the middle with Boston Consulting group issuing a report on durable carbon removals, where the leading buyers are just moving toward the durable category because it does bring certainty of carbon removal and long-term sequestration, right? And there's a price premium associated with that. Okay, so to get to the kind of the final slide here in the sort of general setup of the market, right? And that is, we do have a indication, particularly well documented by Boston Consulting Group, BCG, that buyers want durable solutions. The question is, what can they afford, right? And what you see on the left-hand slide here is essentially a demand function. It's not surprising, right? It's like economics 101, that as price goes down, demand goes up. So what we are seeing here is a strong indication from the buyers that they will buy more durable CDR as the price of that carbon dioxide removal comes down. Okay, so with that, I'm going to turn it over to Hannah. She's going to walk you through the graphite and our carbon casting process.
Thanks, Barclay. So what Graphyte is endeavoring to do is meet that market need for durable, affordable, scalable carbon removal. And the way that we're doing that is through a biker's approach. So we're collecting biomass, which has removed CO2 through photosynthesis. We're putting that through our carbon casting process, which I'll go into a little bit more detail about, but the goal is to halt decomposition. And then we're permanently storing those blocks in our purpose-built storage site where we're monitoring over time. Initially we're starting with using waste biomass, which is in ample supply, particularly near our project in Arkansas, which we'll talk more about. So zooming in on carbon casting and getting a little bit more detail, the process, as I said, starts with collecting biomass. For our project in Arkansas, we're working with a combination of sawmill residues, so think chips, bark, sticks, anything that doesn't go into timber production, as well as agricultural waste. So predominantly where we're working in Arkansas, we're working with rice waste. So things like rice hulls or rice straw that currently just sit around in piles and decompose either into methane or CO2. And in some cases are even burned, putting particulate matter into the air in the region where we're working. We bring that biomass into our facility. We dry it to halt microbial activity. So we bring it down below a water activity at which microbes can't thrive, halting the decomposition. We densify it into blocks. They're relatively small right now. We'll show some pictures, but they're about this big, shoebox sized. We then encapsulate those bricks in an impermeable material, the goal being to prevent water from getting back in to restart decomposition. We can quantify the carbon precisely in each of those blocks through a combination of weighing the block and measuring the carbon content through traditional elemental analysis. We then know precisely how much carbon is in each block, and when we can store it, we then know the amount of carbon dioxide equivalents that we have removed through the process. We have designed a purpose-built site for storing it. We'll talk through some of the details around that, and then we can monitor over time to ensure that there's no re-emission occurring. So that's the overall process. I wanted to double click a little bit on durability and how we think about durability for that. For each of these theoretical principles, we're going through demonstration and testing right now to validate and provide real world data around each piece of it. So to start with the theoretical principle, there's 4 underlying principles that we're working with. The first is that if you dry the biomass and create inert blocks, you can stop decomposition. There's a lot of literature around this. And so what we've done thus far is we've produced dry blocks. We're testing decomposition in a controlled chamber with some partners at North Carolina State, where we can demonstrate that we have effectively stopped decomposition. We also have to keep it dry for carbon casting to work. And so the way that we do that is through this encapsulation material where we're preventing water and gas from getting back into the system and restarting decomposition. And we've spent a lot of time designing our film to ensure that we have very impermeable materials and also very robust materials so that we don't end up damaging them in the process and that they are able to perform the properties that we need them to perform. The barrier then has to stay intact for 1,000 years for it to be durable and be able to maintain those properties over 1,000 years. So it needs to stay impermeable for 1,000 years. There's, again, a lot of literature data around polymer materials over long periods of times, and particularly predicting them out over long periods of time. Most of that literature is folks who are trying to demonstrate that polymers are non-degradable, and therefore they're working towards developing more biodegradable polymers. In this case, we actually want films that last very, very long periods of time. And so we're working with materials that are known to have very, very low degradability, particularly in the conditions in which we're storing them. And we've been performing accelerated aging tests with partners at Argonne National Lab, and then confirming the permeability properties after we age them over time. And then lastly, maximize monitorability. So one of the nice things about our approach is that we're storing the carbon in a very controlled, localized spot, meaning it's not like gaseous CO2 that's spreading in an underground reservoir. It's very local, and we're able to monitor it over time very precisely. And so we're working with an engineering firm in designing our monitoring system, but essentially we're monitoring the headspace within our chambers to understand if there's any production of CO2 or methane over time. And we're in the process of building a test burial chamber to validate all of that in the field. So those are kind of the four principles. The other piece that we're working on in parallel, which is this gray box over on the side, is developing a systems model approach that lets us look at decomposition rates and associated leakage with them, and then use Monte Carlo simulations to predict those out over very long periods of time and understand what the probability for different scenarios over time. This then lets us run out different scenarios, say catastrophe strikes and our whole site gets flooded. What does that look like? And how do we think about those different scenarios over time? We can then use these to compare to other uncertainty comparisons around things like geologic storage or other methods to understand how buyers can feel certain and feel good about the carbon removal that we're performing. So as Barclay said, where are we now? So this is just an update on our Loblolly project, which is literally like in the process. Barclay will be down there next week. So this is in central Arkansas. It's about 30 minutes south of Little Rock in a town called Pine Bluff. And we currently have our pilot line running at a rate of 5,000 tons of CO2 equivalent per year. These are just a couple pictures of some of the blocks being made, some of the packaged blocks. You can see biomass coming out of the dryer onto a conveyor belt. We actually have our ribbon cutting next week. So we're hosting a lot of folks at the site next week to see the line in process. We have employees who are operating the line now. It's been a really, really busy, exciting quarter for the processing site. Our storage site is nearby in a town called Sheridan, Arkansas, and the picture there that just sort of looks like dirt is where the storage site will be. We've purchased 73 acres. About 40 of that is suitable for storage. We have some design for other portions of the land, including drainage ponds and things like that, but we're able to store the equivalents of 1.5 million tons on this site. The site was already excavated, which had some benefits. It was being used for gravel removal, gravel mining and things like that. And so that one sort of, we're not having to cut down any biomass or feel like we're emitting any carbon in the process. And it also lowers the costs associated with excavation because it's already partially excavated. We're in the permitting process right now. So we filed our full permit just about a month ago now, a little over a month ago now. And we're working with the Arkansas Department of Environmental Quality on that front. And we're being permitted we're going down an existing permitting route, being permitted as essentially an inert materials landfill. So that's where we are in terms of the storage site. The construction will begin in May, and we're super excited about everything that's happening. Whoops, I didn't realize that was a video that I put in. Just to give you a sense of the storage site and a little bit more around it, this is kind of the red outline here is the site. You can see the portion that's already been excavated, and then we'll be using these as separate subcells where we can store carbon throughout it. This is then a zoom in of one of the cells where you can see we're taking multiple redundant steps to protect the carbon in the storage, including designing the drainage and the soil and the clay layers throughout to minimize water ingress, as well as what's called a geomembrane liner that gets welded shut once the cell is full. We will also be collecting runoff water from the site. So this will let us test for any sort of environmental hazards or any sort of issues that we might encounter with the water to make sure we're being really, really protective of the land. And then we'll be installing a system to monitor for any generation of CO2 or methane. Barclay, do you want to add anything in this section? Just to give you a chance? Nope. Okay, cool. So one of the questions we get asked a lot is around our LCA and sort of the energy efficiency of this process and carbon efficiency of the process. And I think one of the things that's super exciting about carbon casting is that it has a very, very favorable LCA. And so we've gone through this LCA with Carbon Direct, who did it sort of an outside-in look at our process to try and understand. And what you can see here is a breakdown of the emissions from the project. So some comments about this. One, not surprisingly, the drying is the biggest use of energy. And so this is one of the areas that we're working on trying to improve the LCA. Right now, for our first project, we're using a natural gas-fired drum dryer. The benefits being we can get started right away. It's a known technology, and we can feel confident in the drying levels that we're reaching. But we're already looking into more passive methods like solar drying or other lower energy ways to get the biomass dry. But you can see that that's a big chunk of our emissions. The transportation is also fairly important as far as emissions. Right now, we're transporting biomass to our site and then from our processing site to our storage site. And so that's one where as we scale up, we'll likely co-locate the processing site in the storage site to minimize some of that transport costs. However, I think it's worth noting that the total energy use that we are calculating right now is about 0.8 gigajoules per ton of CO2, which is very, very low energy as far as carbon removal approaches. So you can compare that to DAC, some of the other high energy approaches that are, 10 times that. And so one of the things that is really makes carbon casting scalable is that low energy use. We don't have to wait for a renewable energy project to be co-developed. We can get started and scale immediately. I'll turn it over to Barclay to talk a little bit about scale and where we're headed.
Yeah, so just to kind of connect the dots from the start kind of here to the end, right, is we need a lot of carbon removal, right? And we need it fast, right? That's the whole point of the reference to the WRI study, right? And so as you look at, globally, existing residual biomass, okay, so this is biomass that's being produced, as a consequence of existing economic activities. And it was on the order of about 3 billion tons of CO2 equivalent sitting in those residual biomass sources today. Okay, that's a meaningful amount, right? And it can have a material effect on our climate trajectory, right? Were we to use those residuals for durable carbon removal through the carbon casting process. Okay, so that's sort of one, is just there's abundant biomass, residual biomass available. Second is, if you go to sort of the very sort of practical, perspective here, that we are not engaged in sort of, we are doing science experiments to prove that our process works, right? But we're building things at scale, right? We started out, with our pilot line at 15,000 tons of CO2 per year, right? And we'll very quickly move that to 50,000 tons and onwards from there, okay? And so, what you're looking at here is our roadmap. This is the facilities that we intend to build, right? We can even go faster if the demand function is there. We're not waiting on, major technical breakthroughs or anything to, actually achieve this scale, right? So we got a very credible plan, to be delivering, that is carbon credits issued by registries on the order of 5 million tons per year by 2030. We don't need a lot of energy to do this. The available biomass is out there. It's relatively low capex, compared to other CDR technologies. We think that carbon casting has a very meaningful role to play in the CDR space. That's it. Happy to answer questions from here.
Cool. Thank you guys so much. This has been really interesting so far. I know we're already getting a bunch of audience questions, but I'll just start with a few that we had. Can you just talk a little bit about your kind of personal journey to CDR and to working together on Graphyte?
Yeah, I'll start. I worked in the carbon space for quite a long time, right? So Tank mentioned it at the outset. I was working in geologic sequestration back in the 2010 era for a startup called C12 Energy. Carbon kind of went away for a period of time in the 2010s. I did a lot of remote sensing work in agriculture during that period, and then came back to carbon on the nature-based side with Indigo Agriculture and doing soil carbon there. And what you see with Graphyte, as we were just describing, is kind of a mixture of the best of both of those worlds, right? You get the sort of low energy, low cost nature of photosynthesis doing the work of carbon capture, and then applying engineering to ensure the durability. Hannah?
Yeah. So for me, I had most recently been at Activate, which is an entrepreneurial fellowship program for super early stage science founders. And so had seen a lot of different approaches to CDR coming through both Activate companies and also folks applying to Activate, and had been getting more and more conviction that carbon removal was needed, but more and more worried about sort of the energy and cost of many of the methods being proposed. And so when Barclay reached out to me about Graphyte, I started to get more excited about what they were working on and get very motivated by what was happening and feeling like this was an approach that actually had the potential to scale and have meaningful impact really quickly. And so jumped on board full time. Oh, you're on mute, Megan.
Sorry, having some computer problems today. Okay, no, that's really great. And I mean, always fun to hear people's kind of personal way into it. And how did the specific idea for Graphyte and like this particular approach come about? Because it is a little bit different from a lot of the typical pathways you see out there.
Yeah, so it actually came through a collaboration with Breakthrough Energy Ventures. And so as many of the listeners here may know, Breakthrough is a leading venture capital investor in this space. And I personally know a number of the partners over there, just going back actually to the C12 days. A lot of us were working in the low carbon economy, back in the 2010 era, and continue to work there. And so there's an individual partner over there named Chris Revest. Chris had been thinking a lot about, various forms of CDR, particularly the energy inputs into them, and the fact that may be a major constraint on our ability to do durable carbon dioxide removal. Chris, conceived of the initial idea that we now call carbon casting. He reached out to me. We started kind of workshopping it together, convinced each other that this was actually going to be a very viable, scalable path to doing durable CDR. And from there, Graphyte was born.
Nice. Okay. And in terms of like location selection, I know different states in the US are already starting to think about policy, quite differently. How did you end up choosing Arkansas, and what is it like operating a climate tech company out there?
Yeah, so there's really two answers to that question. So one is I'm from Arkansas. So I was born there. And I'm a proud Arkansan. So, but I left and spent about 15 years in San Francisco, and I really fell in love with the innovation economy in San Francisco in particular, just the coast in general, right? And so when we were founding Graphyte, I said to Chris Revest, the BEV partner, I said, look, it's really important to me that we do this in Middle America. In particular, I want to do it in Arkansas because that's where I'm from. Okay, so that's answer one, is kind of a personal story, is I wanted to prove that you can, build leading edge companies, in the middle of the United States. Secondly is biomass, right? So we talked before, about biomass as the feedstock into our process. When you look across, Middle America, look in Arkansas, what is it? It's a biomass-based economy, right? It's a forestry and agriculture based economy. We plug into those existing industries, effectively taking their trash and turning it into carbon treasures. So that's the other part, is the fact that there's a lot of biomass available across, the middle portion of the United States, other, countries as well. There's a lot of biomass, and so we wanted to start in a place where there's ample biomass.
Yeah. Makes a lot of sense. Okay. And just in terms of the process, so you kind of mentioned different steps of like drying, condensing, and then wrapping the biomass in a polymer. So can you just, I think you touched on it a bit, but like how much of a role does each one of those steps play to prevent any kind of decomposition?
Yeah, sure. I can take that one. So the drying is critical to really halt decomposition. So decomposition is a result of microbes sort of eating the biomass, you might say, and releasing CO2 or methane, depending on the type of microbes. And so if you lower the water activity sufficiently, then those microbes aren't able to perform that action, and you don't get the production of CO2 or methane. And so the drying is really critical to get us below that threshold to halt decomposition. The condensing we do for a number of reasons. One is just a sort of practical reason. It decreases the cost of the process because we can now encapsulate more biomass in a given amount of encapsulating material. We can store more biomass per area, and it makes it easier to handle them. It also has the benefit of making it more difficult for water or oxygen to diffuse back into the biomass. So everything we do is kind of trying to set up redundant layers of protection. And so that's one of them, with the condensing of the biomass into those dense bricks. the encapsulating layer, the wrapping, is the primary protectant that we're applying to maintain the conditions to keep decomposition from restarting. And so that layer, again, is designed to be very, very impermeable and prevent water from getting back into the biomass and therefore restarting decomposition. So it needs to be very impermeable and very non-degradable. And those are the two things that we've optimized it for.
Okay, yeah. So I guess if I'm understanding right, like each of the steps has a role to play. There's some redundancy built in, but like the polymer layer is quite critical. So how do you validate each of the steps and the overall permanence then of the solution? And like, how do things like mechanical damage to the wrapping or things that can happen just out in the elements, how might that affect the permanence?
Yeah. Yeah. So everything we do is trying to make sure that we're providing engineering and protection for the biomass once we've processed it. And so we're doing a number of tests for each section, each portion of our process, and some of those I covered in the talk. But we're doing things like testing decomposition of the blocks themselves once they're dried and created. We're testing the polymer wrapping itself, both initially and then after aging. We're doing mechanical testing, trying to replicate, like, okay, what if we poke it with a forklift? What if we, pick up a pallet of our blocks and now we drop it? Like, how many does that create damage to the sealants, for example? So trying to understand all of the various sort of conditions in which it will be placed. And then the storage site itself is designed to protect against a number of sort of potential for damage or weathering of the material. And so by storing underground, controlling the environment in which it's in, we're avoiding it being exposed to any sort of UV, any sort of like atmospheric incidents, things like that. And so we're sort of taking multiple steps to protect it along the way. We're also, I think, trying to be very rigorous in how we think about modeling those different scenarios. So trying to understand, like, okay, what's the probability of any one of these things happening? How many of those things would you have to stack up in order to restart decomposition? And how would you think about the probabilistic outcomes over time? And so I think, that's all of these types of methods have some risk of reemission, and how you think about what that probability of reemission is gets really critical as you think about whether what you're doing is truly a net benefit. And so we're trying to make sure we take a very probabilistic lens towards it.
Okay, got it. Cool. And then just thinking a little bit about the permitting. So I know you touched on this as well, but it's kind of an issue for most CDR pathways one way or another. So what does the sort of environment look like for this kind of solution? And is the US government or other governments, are they kind of thinking about ways to make this kind of solution easier to deploy? Is that not really on the radar yet? And maybe also how are you hoping it might develop?
Yeah, I'll take that one. So I'm an environmental lawyer by training, right? So I think the permitting part really is very critical, right? And I think there's two really things to think about, maybe three. One is that you have to embrace the community, right? Trying to force a carbon dioxide project on a community is going to fail, okay? And so you have to get in, you have to get to know the community members, you have to, play a meaningful role there, right? And so, sitting from afar and trying to drive it down onto a community is just going to fail, right? And so I think that's number one, is really like embracing community engagement. I do a lot of that work myself as the CEO of the company, okay? Second is, and maybe related to that is the idea that, what are the actual community benefits here, right? Like, what is it, what's in it for the community, right? And so one of the things that's very attractive about, Graphyte's carbon casting approach is the fact that we work with the existing industrial base, right? We are working with the agriculture companies. We are working with the timber companies. That's where a lot of people work, okay, that live in the communities where we are working, right? So you get this sort of inherent sort of alliance that's built because we're helping them to solve some of their problems, these are the existing agriculture and timber industries, to make money over what is now, essentially a waste product, of their existing processes. So having those natural alliances helps to build community support. And the final thing is just kind of understanding how humans work, right? Humans are like heuristic thinkers, right? Where we don't, often sort of work from first principles. We often work like, oh, this thing is like that other thing, and that other thing is okay, right? And so, when you think about the various CDR approaches, the nice thing about graphite's carbon casting process is the closest analogy is inert waste landfills, construction waste landfills. There's on the order of 1,300 or so of those in the United States. They're pretty widespread, okay? And so when you're talking to the community, you can say, well, okay, let's think about this like we think about construction demolition waste, right? It doesn't smell, right? It doesn't cause, lots of public nuisances like birds flocking there or anything like that. It's like, we already know what these things are. We can provide an analogy and say, and we are like, those existing categories, and there's a lot of those, and they're located already near your communities, and they're not causing problems. So I think it's 1, 2, 3. It's really embracing the community. It's building alliances with existing industries in the area, and it's helping the community to understand what the actual effects of your project are, reasoning by analogy where possible.
Got it. Okay, great. Just turning quickly to your TEA, could you talk a little bit about, like people talk about $100 a ton as a typical goal for CDR pathways. Where is graphite kind of at different scales as you scale up? And maybe if you could also talk about the different drivers that are going to change. So anything from like biomass sourcing, costs, transport, economies of scale that might help with the techno-economics.
Yeah. So we're below $100 a ton now. That's with validated costs. Like we have contracts and we're buying biomass and taking it into the site, and we're paying for our electricity and our energy and our transportation. I think the things that we think about to improve that TA over time as we're moving towards more like a $50 a ton, which is our goal, is to get down to a levelized cost of $50 a ton. Some of them I already mentioned, like co-locating our processing site and our storage site will take out some of the transportation costs. Additionally, right now we're at very small block sizes. Getting to larger block sizes, improving the efficiency of the overall process will have impact on the TEA. There are certain economies of scale as the processing line grows that will be important for us. So there's a number of things that will change. The biomass supply, as Barclay said, there's a lot of biomass near us. There's ample biomass within a reasonable radius of our facility to scale to 500,000 tons a year. So biomass supply is not one where we see a big issue in terms of cost or change in the TEA, but overall, there's quite a number of places where we can improve our TEA.
All right. Yeah. And just on that, I mean, I think
just one thing, just before we leave the TA, one thing I'd just like to, encourage us all to think about as an industry. Okay. And that is, if you think about durable CDR, there's a really strong weighting right now to what, your kind of high cost technical, technically challenging maybe solutions is a fair way to say it. And, you look at the early mover buyers, there's a lot of focus on that, sort of some of the policy initiatives at the federal level, a lot of focus there. And one of the things I think, is just for us to important is to think about a more balanced portfolio, right? Like it is important to make investments in those kinds of technologies to see if they can come down the cost curve. But equally important is to start to deploy solutions at scale today, right? So that we can not wait, for 10 years and hope maybe we find a solution out there, right? Let's deploy the solutions that we know will work today, and let's continue to invest the solutions that may work at an affordable rate tomorrow.
Got it. Okay. Yeah, no, that makes a lot of sense. And I guess, one of the questions that I think has been asked in the chat, but also that I was sort of asking about as well, was like thinking about that biomass. You guys are able to access 500,000 tons, I think you said, in the vicinity of where you are. But a couple of people have mentioned like other processes are also increasingly competing for that. And, there's a million different things you can do. And it's a question maybe of what's the cheapest or the best or the most carbon efficient. How do you think about like graphite's particular niche or edge within all the types of biomass and all the types of processes that are being developed?
Yeah, we get asked that question a lot, sort of like what's the highest and best use of biomass? And I think, if you put a carbon removal lens on it, which this crowd probably does, I think the things that are advantageous about the carbon casting process are it's very carbon efficient. So if you think about per ton of biomass, how many tons of CO2 removal are you getting? Carbon casting is a very efficient way to do it. It does that while still maintaining high quality and durability. And so those are very important characteristics to think about when you're thinking about carbon removal related to biomass. One of the other advantages is that we're biomass agnostic. So because we're putting a lot of engineering controls around the storage of the material and preventing water from getting back in a number of different ways. We can work with any type of biomass. So we're not limited to just woody biomass or whole logs. And so that gives us the ability to work with material that other people just don't. So like there's a wood pelleting facility near us. We can take leftover biomass that they can't use. So even when you're thinking about energy production, there's biomass that can't be used. We take the leftovers from other processes. And so being biomass agnostic lets us be very efficient in the way we think about using biomass. And then I think the last one I'll say is, again, because we're taking a fairly engineered approach to the storage site design, we can locate them in most places. So whereas, if you're particularly need arid climate or, some sort of specific geologic feature for your storage, you need salt caverns or whatever, you can become very limited in how you think about deploying. Whereas because we're relatively flexible, we can deploy where the biomass is. And so that gives us an advantage in terms of being able to operate in a lot of spaces.
Yeah. Okay. Well, we have a lot of audience questions. I just wanted to end with one, and then I'll hand it over to Tank. Is there anything you're really excited about that's coming up in the next couple of years, either in the CDR space in general or for Graphyte? What are you looking out for?
Yeah, I'll take that one. I think, and it links back to like how we opened the conversation, and that is that, I really believe that we can solve climate change. Okay, I do. I think the technologies are out there. I think certainly the will is there, right? But I think we've got to start having a bit of a more honest conversation, right? And this is going to be a little bit controversial, right? But if you think about it, go look at global greenhouse gas emissions. They continue to go up, right? Look in the United States, like they're flat. Okay, they're not coming down, right? Look at the CDR space. It's tiny, right? And so if we're going to get serious about this, we've got to get serious. That is, we've got to move beyond small scale, little pilots, demonstration projects, and get serious about widespread adoption of scalable technologies today. It's got to start now, and it's got to start at scale.
Yeah, definitely. Okay, well, I think lots of people have questions now, so I'm going to let Tank go over to those. Tank, whenever you're ready to come on.
Okay, thank you, Mega. Yes, we got tons of questions actually. So I'm gonna try to organize them. Let's start with this first one here that says, you mentioned that locally there is a certain quantity of biomass, but if we're going to the gigaton level, was wondering that apart from Arkansas, what region could lead to sort of an optimal process, or in terms of LCA, what are you seeing in other regions that you think you could go to?
Yeah, so I'll take that one quickly. I think, there's a couple of just good resources. First of all, the USDA recently issued its updated version of the billion-ton report, right? So that's starting to give, pretty good insights into where available biomass is and what types of biomass. Okay, so, the evidence is strong that there is lots of residual biomass, in the economy today in the United States and elsewhere. So I think one, I just point to the USDA billion-ton report as, potential locations of that biomass. Secondly, is I think we also need to think about, it goes to the comment I was just making about getting serious at deployment at scale, is this is not just the United States thing, right? These, carbon removal needs to take place all over the world, right? And we need to understand biomass availability and also energy availability, like how much renewable energy is being deployed in existing markets, and how much can we afford of that energy supply to divert to processes like carbon dioxide removal. So one of the things that I get particularly excited about is because of our low energy input, we can deploy this in the developing world, in particular in South America, Southeast Asia. So as we look at it, we look to expand in existing biomass markets, think, the interior of the United States and other places across the world, particularly South America and Southeast Asia.
Okay, thank you. Great. Now you're talking about the biomass. So one question here is, do you have, I know you said that you are a biomass sort of feedstock agnostic or biomass agnostic, but do you have a preference for a type of biomass, or is there a type of biomass that would yield sort of the greater carbon content?
Yeah, I mean, from a cost perspective, maybe I'll start there. The drier the biomass is, the better we like it. And so certain things like rice hulls, for example, come in very, very dry because they're already piled up in the rice production facility and they're very, very dry. So any sources that are already aggregated and dry help from a costing perspective. In terms of carbon content, yes, there's some variability, some of the agriculture waste is in the lower 40%. Some of the wood waste is in the higher 40% or 50%. So there's some advantages to using the higher carbon content material. And we're learning more about like the specifics of densifying and running it through, like bringing it into our process and what sort of particle reduction process we're going to need for different biomass types. So I think there's more to be learned there. But I would say overall, the main drivers for preference would be dry and aggregated.
Yeah, that does make sense. So now the next question here, let's go with, so we've all seen pictures of these briquettes. So can you give us a sense of how much biomass goes into each of these at the moment? And you did mention that you were gonna sort of making bigger briquettes. So yeah, can you expand on that a little?
Yeah, sure. So we started, like I said, with relatively small briquette size. Each one's about 1 kilo, which translates to about 1.8 kilos of CO2 equivalents. They're like, you can imagine a small shoebox size. We started with that size because the equipment's available. We could purchase it easily and get going. But there's advantages to going larger in terms of, not having to handle thousands to hundreds of thousands to millions of bricks. And also in terms of encapsulating, the more we can fit into a given volume, the cost of the encapsulation goes down. So that's one of the things as we think about scaling, that we're looking at different engineering approaches to getting to larger brick sizes.
Okay, great. Let's see what's the next one here. Sorry. So in terms of the source of heat for drying, what is currently used for your drying process, and in terms of the energy costs involved in the total solution, can you give us a little sense of how much of that goes into energy?
Yeah, let's tag team this one a little bit. Hannah talked about the life cycle assessment, the LCA, earlier. And one of the things that was really important to me is I wanted to run that LCA on kind of a worst case scenario, right? Like using natural gas as the heat source for the drum dryer, right? Using grid electricity, not quote playing any kind of accounting games on the LCA, right? By disguising the emissions, using renewable energy certificates or anything like that. Okay, so we did that, right, to prove that we can have an efficient carbon removal process without even using renewable energy, right? It's still 90% efficient at that level. Okay, so that's how we started. Hannah, I'll turn it over to you to talk about how we will likely evolve to reduce the LCA or life cycle emissions even more.
Yeah, so one of the main things we're looking at is with a drum dryer with natural gas, you're drying in minutes to maybe hours if you have a very large dryer. Passive drying using solar concentrators or solar cells can happen over days. And that's something where it requires investment into the infrastructure, but it's sort of very much established science of how to dry. And so we're looking at different things like that, where we can reduce the cost of drying the biomass over time, both the dollar cost and the energy and carbon cost of it. Because as Barclay said, I think the biggest factor in our emissions right now is the natural gas emissions from the dryer.
Very great, thank you. Another question here I find sort of interesting is that apart from sort of burying, have you guys looked into the briquette being used for other purposes, such as construction or sort of prolonging the lifespan of the biomass and thus building materials?
Yeah, so we certainly have looked into that. And if you think about it, kind of go back to the definition of durable carbon removals, right? And kind of the accepted level of permanence is 1,000 years or more. And then you say, okay, we could certainly use the biomass as a building material, as a bedding material for roads. There's lots of ways that it could be incorporated in the existing infrastructure across the world. But most of that infrastructure doesn't last 1,000 years or more, right? It's roads get dug up and rebuilt, right? Buildings get torn down and rebuilt and so on. And so we started out in kind of using the permanent storage and the sequestration site to demonstrate that you can have durable 1,000-year permanents at less than $100 a ton. As we grow as a company, we will move into the building materials and road materials and so on. But that will likely be it. If it's in that application, it will have less than 1,000-year permits because the application itself has less than 1,000-year permanents. So we didn't want to confuse that at the outset. So thus the focus on the sequestration side. But we do have plans to evolve into those other applications.
Okay, great, thank you. Next question here, I guess let's turn into cost and price a little bit. So you touched upon this, but if we're looking at the trajectory of sort of using biomass for CDR, I think a lot of folks are saying there's going to be maybe not so much as competition, but sort of for the feedstock input. And so do you see a growing price pressure on residuals biomass over time? And how do you see that sort of impacting your profitability, and how do you deal with that?
Yeah, so it's a good question. So there's a number of thoughts around it. One is, biomass cost can go up quite significantly, and our TEA still looks pretty good. And so we think there's a lot of room for us to absorb some increases in price. I think the other piece is, as I mentioned earlier, and it kind of goes to Mega's question around like what's the best and highest biomass. We think the carbon casting process is arguably, certainly for carbon removal, the best and highest use of biomass. And so if we're thinking from a carbon removal perspective, the carbon efficiency and energy efficiency of the process will win out in the end. And so that will be the sort of best way to utilize biomass. And so if you think about every biomass process will have some of that price pressure, it'll automatically then sort of default to the best use or the most efficient use of the biomass over time, which we believe will end up with carbon casting. And then lastly, I think the biomass flexibility that we maintain gives us the ability to use biomass that is relatively unusable for other things. And so thinking about residuals from a lot of other processes that don't have the right heating content or the right ash content or the right chemical makeup for SAF or whatever the case is, gives us some advantages in terms of that price pressure. So I think we're definitely thinking about it and recognize that there's a lot more interest for sure in biomass availability and where to get it and things like that. And there are folks like Low Mist, I think Andy's on the call today, but others who are trying to understand and map out, like looking at different biomass sources and understand more about the marketplace. But we think that we're in a good position as we look at the trajectory of biomass prices over time.
Great. So in terms of your economics, do suppliers companies, or is it possible that suppliers companies pay you to take away their waste, or are you relying sort of on the carbon offset or the carbon removal credits as your source of income?
Yeah, I'll take that one. So we are relying on the carbon removals as our source of income. Okay, so we're not being paid a tipping fee or anything like that. Part of that goes back to kind of the embrace of the other industries, right? Like, I want to build projects. I want the community to want these projects. I want to scale. Okay, and so part of scaling is to making sure that people are making money in the process. And so we pay the biomass suppliers for the biomass on a delivered basis because of that. Okay, that they need to make money in this process as well.
Great, thank you. I probably should have asked this question earlier, but so folks were interested in thinking for drying during the wood shipyard era, wood were often dry, being integrated in seawater or salty brine. Have you ever looked into other methods of drying other than using heat source?
It's an interesting concept, and for sure, I think salt is a potential way to reduce the water activity level to bring the same outcome as far as halting decomposition. There was a PNAS paper relatively recently from Harry Deckman and Jablanovic about the concept of storing in salt, specifically storing biomass in salt to bring down the water activity. I think as with all things, as you think about scaling some of these, it becomes an interesting question, like, if you truly think about scaling to the level of CDR we need, you're talking about like the salt production of the globe. And so things like that, I think, become important as you're thinking about these different drying methods. But yes, I think like getting creative around drying is something that we are definitely spending time on and trying to understand, like, how do we do this in a way that isn't very energy intensive? And so whether it's salt or other things, I think, yeah, for sure, different drying methods is something that's of high interest to us.
Great, thank you. And another LCA question is, does your LCA include the production of the polymer or the construction of the storage site? And I would like to blend that into another question that can you sort of talk about the accounting for methane in your method?
Yes. So to the first part, yes, the LCA includes the emissions associated with producing the polymer. We are currently working with a fossil-based polymer through traditional supply chains. Again, for the ease of getting started and having material supply chains established. We are also looking at bio-based polymers and moving off of that. But for full transparency, that's where we are. And we are including the emissions associated with that in the LCA. Similarly, the emissions associated with the storage site are all included. Like I said, our LCA was done by Carbon Direct. And so they have kind of a very thorough process to make sure we're including everything. And so we also want to be really transparent and clear about everything that's included. What was the second part of the question? Sorry.
On methane.
Oh, methane, yes. So we are not accounting for any methane avoidance. We are assuming that all of the carbon that we are removing is carbon CO2 equivalents. In reality, there is actually, for sure, methane avoidance because much of the biomass sits in piles that are wet and emit methane as they're degrading. But for conservativeness, we are not accounting for any avoided methane emissions in our LCA.
Okay, thank you. And then I think last question. Oh, sorry, go ahead.
I was just going to say one other thing. If you go, if you're looking at the sequestration site itself, right, in our process, right, we are, have a leak detection system to ensure there is no methane production. So I just wanted to get that in as well. We're not accounting for any avoided emissions from the methane that, where the biomass is decomposing in the pile. And we are testing to make sure there is no methane emission from our process.
Yes, good addition.
Okay, so the last one here is on sort of the permits, and this person is your storage site is a class 3 landfill, and can you talk to us about a little bit more about landfill permits?
Yeah, so I'll take that one. So yes, it is a class 3 landfill. That's the way we're permitting it, right? It's not because it's necessarily a landfill, but it's the closest analog in the existing permitting, regiments that are out there. Okay, and so it goes to what I was talking about earlier with respect to, the nearest analog is inert waste going into landfills. In where we do depart from the engineering standards required under class 3 is we actually go above and beyond them, right? In that we are having an HDP liner both on the ground level, if you will, right, as the floor of the sequestration site, as well as at the ceiling level, right? We put, HDP at the bottom, we put it at the top, we weld it closed, so you essentially have a underground carbon tomb where the material is stored. So yes, that is the permitting pathway we were using in Arkansas, and we are going above and beyond that from an engineering perspective to ensure that the carbon is durably stored for the next 1,000 years.
Okay, I think that's all the time we have, so I'll turn this back to Mega.
Great. Thank you guys so much for joining us. This has been really great. Appreciate you coming on. Great. For everyone watching, next week on This is CDR, we have our 100th episode. Very exciting. When we'll have Dr. Phil DeLuna of Deep Sky on to talk about building infrastructure for carbon removal. They've announced a bunch of cool partnerships lately, including at least one This is CDR alumni. So check them out and please do register for next week. Thanks for being here and hope to see you next week. Bye.